Hello, my name is Kelvin from Group 4, and today I'll be explaining on our main problem statement, which was the mixing tank problem. So in this case, it's imagine if a tank that holds 100 liters of water contains 1 kilogram of salt. So brine flows in at 5 liters per minute, and the concentration is 0.2 kilograms per liters. So the well mixed solution flows out at 5 liters per minute. So from this, we can already understand what is it that we actually need to solve. What is the scenario and what is it that they're actually asking. So in this case, the mixing tank is a very usual problem where we actually try to identify certain variables such as the inflow rate, which is the Rn, which is 5 liters per minute, the inflow concentration, which is 0.2 kilograms per liters, the outflow rate, as well as the QT. So QT is actually the main target variable, which is the amount of salt in the tank at time t. So we actually want to understand what is the amount of salt that is present at a certain time when water comes in and water goes out. So the initial condition that is given is actually Q0 equals to 1 kilogram. So that is the initial amount of salt. So from there, we actually try to understand what is the amount of salt at certain conditions. So to do this, we actually need to derive the ODE. So basically, this is just a differential equation, which is the rate of change of salt over time. So the formula is the inflow rate multiplied by the inflow concentration minus by the outflow rate multiplied by the Q, which is the amount of salt, as well as V, which is volume, which is fixed at 100 liters. So once you input in the values of the inflow rate and the inflow concentration and Q and the outflow rate, we can actually see that the derivation results in FTQ equals to 1 minus 0.05 Q, which is basically just a very simple linear equation, which tells us that um, the more that the salt we have in the tank, the faster that it leaves through the outflow. So we're going to use this function to actually predict the salt levels numerically. So there are multiple methods that were given, but the one that we decided to choose was actually the RK4 method. So within the RK4 method, it's actually just a method to find the amount of salt at t equals to 1 as well as t equals to 2. So we'll be using a step size of 1, and we'll be identifying two different iterations, which is Q1 at t equals 1 as well as Q2, which is t equals to 2. So when you look at Q1, the K1 is actually just the beginning slope or beginning increment at our starting point, which is T naught and Q naught. So we just add in the value, the initial value that's given, and then we identify K2. So K2 is actually just like the next iteration or the next slope or the next increment where we actually need to use that to estimate the midpoint. Same with K3 as well. We just refine the midpoint using refine the midpoint that was given using K2 to identify K3. And in K4, we actually have the n interval using K3. So what we do to identify the whole iteration is actually Q1 equals to Q naught plus 1 over 6, and then K1, 2K2 plus 2K3 plus K4. So this is just like the whole combination that we get for the first iteration, which results in 1.92664 kg. So we continue this with iteration 2, where Q2 at t equals to 2. So we repeat the process, but now our starting salt is actually 1.92664. That is the initial value that we got from iteration 1. So we use that to find our K1, and from there we use it to find, we can notice that we're on the right track because the K1 for iteration 2 is actually very similar to the K4 for iteration 1. So we know that it's actually continuing the curve or the trajectory of the iteration. So we keep this pattern going by finding K3 as well as K4, and then we combine all of them together into to find Q2, which is the second iteration total, and we identify that we arrive at 2.80809 kg. So we notice that as time goes on, the amount of salt is increasing because the value of Q is increasing lah. But then we also notice that the slope or the K values is getting smaller. It's decreasing and it's getting smaller. So this shows that the system is actually starting to approach an equilibrium already. So because we've done this manually, we can also do this in a code format. So the code that I decided to choose was Python compared to C as well as like MATLAB. I thought Python was a bit more easier to understand as well as a bit more easier to implement. So when it comes to the Python implementation, the first thing that we actually did was to define the the function, which was the FTQ. That was actually the first thing that we decided to do for the ODE lah. So we return 1 minus 0.05 times Q because that is actually the function. Next thing we defined was actually like the main method, which is solving RK4, as well as like the variables that we've already put there, which is the T naught, Q naught, H, and steps, which later will actually fill in the respective values. So we can actually see that we've created two lists, which is T equals to T naught as well as Q equals to Q naught. So these lists basically act as the database to store every result that we calculate. And the next thing that you can notice is actually the loop. So for I in range and steps, which is basically just the steps to get the iterations. So this one is basically just a way for us to tell the computer, hey, we want to repeat the RK4 process based on the number of iterations that we want. In this case, we're looking for 2 iterations. And inside the loop, we've set Tn equals to Ti and Qn equals to Qi. So this just ensures that the values that we're using are actually the most recent data, so we can calculate the next one correctly. And then you have the K calculations. The K calculations is basically similar to K1, K2, K3, K4. Here you can notice that there's 0.5 in K2 and K3. So it basically just tells us to evaluate the slope at the midpoint. While K4, if you notice, it uses the Tn plus H. So it tells the program to evaluate the slope at the full step. And then you go on to Q next, which is basically just the iteration value. So from there, we can actually get the amount of salt present based on like the formula that we put. So this just calculates like the amount of salt that's present. So the next one that you can see is actually uh, the F strings, which is basically just the print, like how we actually want to print the values that we have. So the value of K1, K2, K3, K4, and then we put 5 F, basically just to tell the program like, hey, we want to round it out to 5 decimal places, which matches like what we're actually looking for based on the manual calculations as well. And finally, the script just calls the function that we have using based on the specific tank value. So like I mentioned, the initial value for T, the initial value for Q, the number of iterations that we want, and the step size as well. So this really works well because when we use this code, it really depends, like, are we looking for 1 iteration? Are we looking for 2 iterations? Because maybe if you want to do 1, 2 iterations, it's a bit more easier. If you want to do it, like it's doable manually, but why we actually implement code is that maybe we want 1,000 implementations. Maybe we want 100 implementation, 100 iterations, sorry. So when we can do that amount of iterations, we can better identify the flow as well as like the sequence, and it's a bit more easier compared to doing it manually as well, compared to doing it by code. So the next thing that we would like to show is actually just the analysis for the graph. So you can notice here that based on the visualization, we actually compared the exact solutions as well as the solutions that we got from RK4. So here you can notice that RK4 almost overlaps with the exact solution, meaning that it's very accurate for us to implement RK4 because it's actually very, very similar to the exact solution, or in this case, the exact amount of salt that's present in the tank. So we don't really get much error present whenever we do RK4, which makes it a very how to say, a very accurate, very reliable way to actually measure what is there. So the main implementation that this happens in real life is obviously, I think, water treatment plants. Because within water treatment plants, we can actually manage to see what is the concentration of minerals or purification chemicals inside the reservoir. So the main thing is obviously when you want to purify water, we use a specific concentration of chlorine because chlorine helps to purify the water. So engineers pump in brine, which is salty water, or treated water at a control rate, which is the R in, which adds to the total mass of the substance. So how is it that we actually want to maintain the water quality? Is that the tank is continuously mixed and then the water is simultaneously pumped out. This is very similar to the actual question that we're given. But in this case, how is it that we actually use alpha 4? Is that it's mainly just to predict how the salt level Q changes over time. So engineers actually use these numerical methods because they actually want to accurately identify what is the change over time. So it allows them to determine exactly when the water will reach a steady state, basically when there's an equilibrium, when it's balanced. So when it is balanced, it ensures that the salinity, like the chlorine amount that's present inside the water, is safe. It doesn't exceed anything, any safety thresholds, and it prevents any damage to the infrastructure of the tank, as well as prevents any harm to the consumers that are actually using the water. So when it comes to like the main implementation of how this question is used and how this numerical method is used, I think this is one of the more accurate ones. Because we use this in a day-to-day life, especially engineers when they want to identify how safe they want the chlorine or the purification chemicals, the amount to be within the water. So I hope that is able to explain everything that we have conducted in this project. Thank you so much.